The intensification of climate change has led to severe land degradation, reduced agricultural productivity, and declining soil health in many regions worldwide. The increasing frequency of extreme weather events, such as prolonged droughts, erratic rainfall, and rising temperatures, has intensified soil vulnerability, making it difficult for farmers to sustain food production. In response to these challenges, biochar has emerged as a promising soil amendment capable of improving soil resilience in climate-stressed regions. Derived from organic biomass through pyrolysis, biochar not only enhances soil structure, water retention, and nutrient availability, but also acts as a carbon sink, mitigating greenhouse gas emissions. The potential of biochar to transform degraded landscapes into fertile lands has gained significant attention from researchers, policymakers, and farmers alike. This documentary explores the science behind biochar, its applications in climate-affected regions, and real-world case studies demonstrating its effectiveness. Biochar is a carbon-rich material produced through the thermal decomposition of organic biomass in an oxygen-limited environment. The process, known as pyrolysis, converts agricultural residues, wood chips, manure, and other organic materials into a stable form of carbon. Unlike conventional organic amendments, biochar has a highly porous structure that improves soil aeration, moisture retention, and microbial activity. Its chemical composition varies depending on the feedstock used and pyrolysis conditions, but it generally contains essential nutrients such as nitrogen, phosphorus, and potassium, which contribute to soil fertility. One of the most remarkable properties of biochar is its ability to enhance soil-cation exchange capacity, allowing it to retain essential nutrients for plant uptake. Studies have shown that biochar can significantly reduce nutrient leaching, making it particularly beneficial for sandy soils that struggle with nutrient retention. Moreover, biochar alters soil pH, buffering acidic and alkaline soils to create a more suitable environment for plant growth. These unique characteristics position biochar as a critical tool in rehabilitating degraded soils and promoting sustainable agriculture in climate-stressed regions. Soil resilience refers to the capacity of soil to withstand and recover from disturbances such as droughts, floods, and nutrient depletion. Climate change has exacerbated these threats, leading to declining soil productivity and increased vulnerability to erosion. The introduction of biochar into agricultural systems has demonstrated its potential to mitigate these challenges by improving soil moisture retention, enhancing soil microbial communities, and reducing greenhouse gas emissions. Drought-prone regions are particularly susceptible to soil degradation due to water scarcity and high temperatures. Biochar has been shown to enhance water-holding capacity by increasing soil porosity, allowing it to retain moisture for extended periods. Research conducted in sub-Saharan Africa, where droughts have severely impacted food production, revealed that biochar-treated soils retained up to 40% more moisture compared to untreated soils. This increased water retention reduces plant stress during dry spells, leading to improved crop yields even under adverse climatic conditions. Similarly, in flood-prone regions, biochar improves soil drainage by preventing waterlogging, which can lead to root suffocation and reduced plant growth. Its ability to enhance soil structure prevents compaction, allowing excess water to drain effectively while maintaining optimal aeration for plant roots. These properties make biochar an essential soil amendment for building resilience in areas prone to extreme weather fluctuations. In sub-Saharan Africa, where soil degradation and water scarcity pose significant challenges to agriculture, biochar has been successfully integrated into farming systems to improve soil health and increase crop productivity. A study conducted in Ghana demonstrated that maize yields increased by 40% when biochar was incorporated into the soil compared to traditional fertilization methods. Farmers reported better soil texture, improved nutrient retention, and enhanced resistance to drought conditions. Another successful case study comes from Kenya, where biochar was introduced as part of an integrated soil management strategy in coffee plantations. The results showed that biochar application led to a 30% increase in coffee bean yields, while soil tests indicated a significant reduction in acidity levels. Given the high acidity of many African soils, The ability of biochar to neutralize soil pH contributed to better nutrient availability and overall crop performance. Beyond increasing yields, biochar has also provided economic benefits to smallholder farmers. In Malawi, a community-driven initiative focused on converting agricultural waste into biochar for soil amendment. The initiative not only improved crop productivity, but also created additional income streams for farmers who sold surplus biochar to neighboring regions. This dual benefit of improving soil resilience while fostering economic empowerment highlights the potential of biochar in transforming agricultural landscapes in developing countries. Rice farming in Southeast Asia is heavily affected by soil degradation, water scarcity, and methane emissions from flooded paddies. Biochar has been explored as a solution to address these issues while promoting sustainable rice cultivation. In a large-scale field study conducted in Vietnam, researchers found that biochar application reduced methane emissions by 50%, while simultaneously increasing rice yields by 15%. The reduction in methane emissions is particularly significant, given that rice paddies are a major source of greenhouse gases contributing to climate change. Similarly, in the Philippines, biochar was introduced to rice farms to enhance soil fertility and reduce reliance on chemical fertilizers. Farmers observed a noticeable improvement in soil structure and water retention, leading to better root development and increased grain weight. These findings underscore the role of biochar in promoting climate-smart agricultural practices that benefit both farmers and the environment. The arid and semi-arid regions of the Middle East face extreme challenges in sustaining agricultural productivity due to high temperatures, low organic matter, and excessive soil salinity. Biochar has been tested as a soil amendment in desert agriculture to improve soil moisture retention and fertility. In a pilot study conducted in Saudi Arabia, researchers applied biochar to sandy soils used for date palm cultivation. The results showed a 60% increase in water retention and a significant reduction in soil salinity levels, enabling healthier plant growth. In Israel, biochar was introduced to greenhouse farming systems to reduce irrigation requirements and enhance nutrient uptake efficiency. The findings revealed that biochar-treated soils required 30% less water compared to conventional farming methods, making it a viable solution for water-scarce regions. These case studies demonstrate how biochar can be instrumental in supporting food security in some of the most inhospitable agricultural environments. Beyond its immediate agricultural benefits, biochar contributes to long-term environmental sustainability by sequestering carbon and reducing greenhouse gas emissions. Biochar's stable carbon structure allows it to remain in the soil for centuries, effectively removing carbon dioxide from the atmosphere and mitigating climate change. Studies have estimated that large-scale biochar adoption could offset up to 1.8 gigatons of carbon dioxide annually, making it one of the most effective carbon sequestration strategies available. Moreover, biochar application reduces nitrous oxide emissions, a potent greenhouse gas released from nitrogen fertilizers. In trials conducted in Europe, researchers found that biochar-treated soils emitted up to 70% less nitrous oxide compared to untreated soils. Given that agriculture is a major contributor to global nitrous oxide emissions, integrating biochar into farming systems presents a viable strategy for reducing the environmental footprint of food production. Despite its many benefits, widespread biochar adoption faces several challenges, including high production costs, lack of awareness, and limited access to suitable biomass feedstocks. The cost of biochar production remains a barrier for smallholder farmers, particularly in developing regions where financial resources are constrained. Efforts to develop low-cost, community-based biochar production methods are crucial for scaling up its application. Additionally, there is a need for further research to optimize biochar formulations based on specific soil types and climatic conditions. While biochar has demonstrated positive impacts in various agricultural settings, its effectiveness depends on factors such as feedstock selection, pyrolysis temperature, and application rates. Continued scientific investigation and knowledge-sharing platforms will play a crucial role in maximizing biochar's potential. Looking ahead, policy support and financial incentives can drive the adoption of biochar as a sustainable agricultural practice. Governments and international organizations can promote biochar use through subsidies, carbon credit programs, and farmer training initiatives. By integrating biochar into national soil management strategies, countries can enhance food security, combat climate change, and promote sustainable land use. Biochar represents a transformative solution for improving soil resilience in climate-stressed regions, offering benefits that extend beyond agriculture to environmental sustainability. Its ability to enhance soil fertility, retain moisture, reduce greenhouse gas emissions, and support climate adaptation makes it a powerful tool in the fight against land degradation. Real-world case studies from Africa, Asia, and the Middle East demonstrate the tangible impacts of biochar on food security and soil restoration. While challenges remain in scaling up biochar adoption, investment in research, policy support, and farmer education can unlock its full potential. As climate change continues to threaten global agriculture, biochar stands as a beacon of hope for resilient and sustainable food production systems.